illustrate part of the properties of the primal group problems, and this is just an example of the primal group theory. And I cannot remember whether I have mentioned this example before, and this is just an example to give you a little idea about what is the primal problem and what is the difference. And one problem is called housewife problem. Have I talked about this before? Okay. So this is the very general problem. Assume like there is a housewife and he wants to raise the kids, right? If he wants to raise the kids, then he has the options to buy those vegetables, those dairy, those meat in order to satisfy the kids' nutrition needs. Right? And for the vegetables and for the dairy and for the meats, they have different prices. Right? So the housewife's objective is simple. Just would like to satisfy the nutrition needs while trying to minimize the total cost. For example, she will like say like buy X units of meat, like we use P1 to denote the price of the meat per unit. And he would like to buy Y units of vegetable, and may say like buy Z units of, let us say, dairy, something like this. This is the selections of the housewife, and this is the total price that she would like to pay. And her objective is just to minimize the objective function. And of course, subject to the constraint. The constraint is that you need to provide enough nutrition to the kids. And let us say like X is the units of, let us say, the meat, and the meat may have say like 1% of some particular nutrition, and for the Y units of the vegetable may have 2% of some particular nutrition. Let us say vitamin C, for example, and like Z units of the dairy has like 10% of the particular nutrition. And this is the nutrition that you can get from the food, and you just want to be larger than some value. For example, A. A is the basic demand for the kid. Yes?
No, I'm just stretching.
Okay. So this is the very typical problem, and there's no interesting part of this problem. It just would like to satisfy the nutrition needs by providing particular units of the food, and the objective is to minimize the total cost. And this problem, we can say it is the primal problem. Primal problem. And we would like to say, like, assume like there's the housewife. She wants to save the money by guaranteeing that the kids get enough nutrition. Well, of course, that you can solve this primal problem, and there's another problem which is not at the first glance. There's no relationship between the other problem and this one, but you will eventually realize that there exists a relationship between those two. As you can think about this one, and the price for the meat, for the vegetable, and for the dairy will be the market price. And the market price will be, like particularly in economics, they were determined by the demand and supply. And assume like we consider another problem. Another problem is that assume you are a drug dealer, not that kind of drug. That is so like assume you want to provide some drug, okay? And you have the advertisement saying like, okay, if your kid has 1 kilo of this drug, then he gets sufficient nutrition. You don't need to eat anything. And assume like you would like to sell this kind of drugs, then the question is that what is the price you want to set for the drug? If you set the price as too high, and of course that if many people buy your drugs, then you earn money, you get a profit. And if you set the price as too low, of course that the profit will be lower. However, there is the conflict, because that is that if you set the drug price is higher, okay, and I believe that the housewives want to buy your drug because that this is her budget. She wants to guarantee the nutrition needs, right, subject to the objective function. Okay, the objective function, the results, the minimum value of this result is the money paid by the housewife. And if you drop data, then you want to maximize, let us say, you want to maximize the price. Let us say P. This is the price of the job, and you cannot set the prices. You want to set the price too high in order to learn more profit, but this price should be lower than this one, right? That makes sense. The job price should be lower than the money paid by the housewife, and then they will believe that okay, they can pay less money to buy your drug in order to satisfy the nutrition needs. So this is the price, okay, determined by the demand and the supply. And this is the price determined not by the supply and the demand, but determined by the other prices. So sometimes we call this is the shadow. I cannot remember its name. Okay, sorry about that. Shadow is the shadow price. I cannot remember exactly what is the name, but that price is not determined by the market. So, sorry. So this is the primary problem, and this is the dual problem. So you can realize that these two problems are not relevant to each other before you examine them carefully. But if you examine these two problems carefully, you realize that the objective of one problem, whenever it is optimized, is the objective of another problem whenever it is optimized. And one problem is to minimize the objective, the other one is to maximize the objective. So if you look at the price, okay, like that, then you realize that, oh, the price, let us say the money. Like that, then you realize the primal problem is to minimize the total cost. So the primal problem is to minimize the cost in this manner. And the dual problem is to maximize the objective in another manner like this. And whenever they reach their optimality, they will reach the same value. And this value will be optimal for both primal and the dual problems. So this is only a core example, particularly if you learn the macroeconomics, then whenever you learn the game theory part, this will be the first core example that you need to learn about. Trying to figure out that for two problems, and they got the same optimal values whenever one is to minimize, one is to maximize. And you can call these two problems a primal problem and dual problems. This is primal and dual theory, part of the primal and dual theory. Another one is that, I guess you may heard about this one, is more like the zero-sum game, okay? Assume like I play a game with you, and then I have a coin and you have a coin, okay? And if we show the same size of the coin, say like a hat, then I pay you $1. And if we say different size of the coins, so, and then you pay me $1. So what is the strategy if you would like to maximize your payoff, okay? So in such a game, then my objective is to maximize my payoff, and your objective may be to minimize what you paid to the other guy. So the best strategy for me and for you will be randomly select one side, and for each side with the probability of 1/2. And only in this case, and my expected payoff will be $0, and for you the same one, okay, $0. So in such a kind of game, so it's like zero-sum games, then there always exists an equilibrium, such that for one problem, if you want to minimize the total cost, the other problem want to maximize the total revenue, and they reach the same expected payoff of 0 for both of them. And this is the two-person zero-sum game. And you could, of course, you could generalize it to 3 people or n people. And Nash gave the famous results that for n people game, and you could always find out one equilibrium if the number of people is finite. So that is, he won the Nobel Prize based on this result. And of course, that based on 3 main results, and this is one of them. So as you can imagine, that the primal dual theory, particularly in computer science or in math or even in economics, they play a very important role, because that people could look at the problem from another perspective, and then try to figure out the underlying structure similar to both problems and figure out the relationships. And the network flow is the first example of the primal dual theory, and it illustrates the importance. So like, one problem is we would like to find out the maximum flow. Another problem, which is his dual problem, is to find out the mean count problems. So whenever we will introduce these terms later, but at the first glance, we look at the problem in this way. One problem is to find out the maximum flow, and then we provide an algorithm. We cannot show the algorithm is correct only if we show that its dual problem is optimal whenever the solution is got. So if this is the primal problem, we minimize its total cost. And we do not know whether this cost is minimized if we are running some algorithm, that is some algorithm A. So how do we prove that the solution we got from the algorithm A is correct? We do not look at the primal problem. Instead, we look at the dual problem. We understand that the dual problem objective will never exceed the primal problem solution. So this problem's objective, the dual problem's objective is maximized. But for any case, it cannot, its maximized value, even if it is optimal, it cannot exceed the minimum value of the primal problems. This is the feature or property of the primal dual theorem. So if we cannot prove that the primal solution is optimal, then we look at the dual problem and we show that the solution got by the primal problems is optimal to the dual problems. And then that implies that for the primal problems, you have found out the solution. So that is why we need to introduce the primal dual theory before we talk about the problems. We will introduce those terms soon. So for the Van Voxen develop the maximum flow problem, we'll introduce that algorithm after we introduce the problem. And then the maximum flow mean cut theorem indicates the primal dual features. We'll talk about this one as well. So this is the advanced algorithm, capacity scaling algorithm, shortest augmenting path. This algorithm are improved version of the Van Voxen algorithm, and I don't want to cover those. Okay. They just fasten the algorithm's running speed, but essentially that they are the same kind of algorithms. And sometimes people do not call it the Van Voxen algorithm. Instead, they call it Van Voxen scheme, because that is the type of schemes that may involve many algorithms. And like the Balopin flows and the unit capacity synchronization, for all of those algorithms, they consider try to improve the running cost of the Van Voxen algorithm, or consider some special cases. I don't want to cover those algorithms, and today I will try to finish the introduction of the problem, the algorithm, and some of the maximum flow mean cut theorem. And this Thursday I will try to complete the proof, and I try to provide a few examples how do we calculate the maximum flow. And but next week we will use these algorithms to solve some applications. So before we talk about the maximum flow problem, let us look at a few terms. One is called the flow network. And eventually you will see the term network more than the term graph. And particularly, you know that in the current era, when people will see like the graph sometimes will be expanding very quickly, that it will involve millions of vertices. And sometimes you may also need to consider the dynamics of the graph. And for the graphs that we have talked before, we consider the shortest path problem, the minimum spanning tree, and whether the connectivity between two vertices, etc., etc. So for those graphs, sometimes we found that those graphs are relatively static. For networks, this is the type of graph such that you may consider the dynamics of this graph. The graph may be changed. The graph may be evolving over time. And sometimes there are some other materials that go in on this graph. And for this particular type of graph, such that you may assign flows over the edges. And this is special type of graph, we call it a flow network. So this is the example of the flow network, okay? And sometimes if we consider the dynamics of the graph, we use the term network. So we consider a directed graph with a source and with a sink. The source is S here, the sink is T. Okay. And also this is the directed graph such that all the edges are directed, and on these edges there's some value assigned with this image. And the value here is not the weights. The values are not the weights. Rather than this is called the capacity. And we will see the capacity. You can imagine flow network is more like a network of pipes. For example, this is some company providing water, and all of them are houses. And here is the pipe connecting the company and the house. And the value here is the capacity denotes the pipe's capacity. It means like how much units are, how many units of water can be pushed from the source to this house per unit time. So you can imagine like this. So for the capacities, they are non-negative integer capacities. So this is the flow network, such that if you have a network like this, and if you have all the pipes, water pipes, on the network like this, then you may imagine that at some times there are some water that can go from the source to this house, and may go from this house to this house, etc. So this is the flow network. So what is the mean cut problem? So we already met the concept cut, and in summary, a cut is a set of edges such that if you remove these edges, then the graph is partitioned into two or more parts. So if we consider there's graphs, then for these three edges, they consist of a cut. Because that if you remove these three edges, then the source S is disconnected from the other vertices. And there are multiple cuts. For example, these three edges consist of one cut. And these three edges consist of another cut. And also these edges, 1, 2, 3, 4, 5. These 5 edges, if you remove them, the graph is 6. 1, 2, 3, 4, 5, 6. If you remove these 6 edges, then the graph is partitioned into 2 parts. So a cut just represents a set of edges such that if you remove them, then the graph is disconnected. Well, if you remove those edges, then there is the capacity of the cut, which is defined by the total capacity of the edges going from one side to the other. And realize the case that if you select these 3 edges and if you count the capacity of these 3 edges, then you may imagine that this is one part and all of the other vertices consist of the other part. So these 3 edges connecting this part and this part. And the cut of this capacity, the capacity of the cut, this cut is defined by the total capacity going from this side to this side. So for this particular instance, the capacity of the cut is 10 plus 5 plus 15, which is 30. This is the definition of the capacity of the cut. And if we mentioned before that is if you select this set of edges, right? If you remove them, then you still have a cut. And 1, 2, 3, 4, 5. These 5 edges consist of a cut. And also, however, whenever you count the capacity of this cut, you consider the capacity of those edges going from this part to this part. So if you look at the capacity of this cut, then you count 10 from this part covered by the cut, from this part to this part, 10. You do not count this edge into the cut capacity because this edge is going from this side, this part, to the cut. And you count this one, you do not count this one, and you count this one. So for those edges that 10 plus 8 plus 16, this is the total cut capacity of this cut consisting of 5 edges. You may imagine that the capacity of this cut could be regarded as the total water that could be poured from one side to the other. So you only consider those pipes going from the water side to this house side, right? You do not count the edges going from the house side back to the water side. So this is the cut capacity. The minimum cut problem is to find the cut was the minimum capacity. So this is the problem. And if you know how to define the capacity of a cut, so given a flow network, given the capacity of those edges, then the objective is that whether you could figure out a cut such that the capacity is minimized. Any questions so far here? This is the min count problem. And if you imagine that the graph is more like a water pipe graph, and then the problem of the min count problem is to find out the set of pipes such that you cut them off, and then you got the little water, the fewest water from this side to the other side. So this is the min count problem. Now we talk about another problem. We introduced the min count problem. We didn't give the algorithm. We didn't provide any analysis. And then we talk about another problem, which is called maximum flow problem. And we will see the relationship between those two. As I have mentioned, right, one of them may be the primal problem, the other one may be the dual problem, and they have different objectives. Whenever we find out the optimal value for one problem, we immediately get the optimal value for the other one. So the maximum flow problem is defined as this. And consider this is the pipe flow, water flow, and this is all the pipes. And we know that the capacity of this pipe, and we can imagine that the water, whenever it goes along the particular pipe, the total amount of water cannot exceed the capacity of that edge. And the water that is going on along one pipe is called the flow. It's called the flow. For example, like in this graph, we use we use two numbers. The first number denotes the flow. The second number denotes the capacity. And we have to guarantee the capacity restriction such that at any time the flow cannot exceed the capacity of that pipe or of that edge. So for this given instance, we realize that when all the values, all the flow values are less than the capacity of that edge. So this is capacity constraint. Another one is that imagine that we want to push water from the source to the sink. And all the intermediate node cannot reserve any water. They do not reserve any water. It means like if you give me alpha units of water, then I pour off alpha units of water as well. So this is called the flow conservation restriction. And if you look at this flow given in this instance, you can realize that for this particular node, right, it has 3 incident edges, 2 incoming edges, 1 outgoing edges. And for those edges, they satisfy the capacity restriction such that the flow value is less than the capacity value. Flow value less than the capacity value. And for the flow conservation restriction, the incoming flow is 10 plus 0, right? So that is the total water that you push into this vertex. So 10 plus 0 will be the incoming flow. The outgoing flow is 10 as well. So the incoming flow equals to the outgoing flow. Okay. So for any vertex, rather than the source and the destination, they should satisfy this feature. So this is the 2 requirements whenever you find out or whenever you define a flow for a given flow network. So, however, for S, the source, okay, there's no incoming flow, there's also outgoing flow. So the total outgoing flow will be 10 plus 5 plus 10, which is 25. And realize that for all the intermediate node, the incoming flow equals the outgoing flow. And in other words, it means like for any intermediate node, they do not generate water. The water only is pushed out of the source, and for any node, intermediate node, they do not generate water. So all the water pushing out of the source will be ending up at the sink. So if you look at the incoming flow to the sink will be 5 plus 10 plus 10, which is 25 as well. So you could imagine that this is the black box, okay, other than the vertex S, source S, and the sink B. This is black box, we do not generate the water. So the number of the units of the water that you push out of the source will be here. So this is the definition for ST flow. So given a source, given a destination, given a source S, given a destination think T, then you have ST flow. So the value of this flow is defined by the total flow outgoing from the source. So like whenever you have a flow here, and the flow satisfies the 2 restrictions. One is the capacity restriction, another one is the flow conservation restriction. Say like for the flow value is less than the capacity value, and for any vertex rather than the source, I think the incoming flow equals to outgoing flow. Okay. So whenever you have a flow, then you know that what is the flow outgoing from the source. You can sum up all the flows here, so this is 25. So the value of the flow for this given flow is defined by the total flow, value of the flow that is outgoing from the source. So the maximum flow problem is to find out the flow as the maximum flow. That means like if we have the water pipes here to restrict how much water that can go along that path, then if we want as much as water, then how much water that you can push along this path. So this is the maximum. So far, we introduced 2 problems. One is the mean time problem, and one is the maximum flow problem. For the mean time problem, there's no flow. We only have the capacity of those edges. And whenever you have a path, then you can define the capacity of that path by summing up the capacity of those edges going from the source side to the sink side. And the mean count problem is to ask you to find out the minimum count. Okay, we'll first find out the count with the minimum capacity. And we have mean cut problem, and we also introduce a maximum flow problem. And for the maximum flow problem, we want to maximize the flow. So for these two problems, they work on the same flow network. They are looking for different objectives. And we want to see whether there are some relationship between these two problems. One we can call it primal, and one we may call it a dual, such that the objective of these two problems are the same. So this is the one that we are going to prove. So as long as you can show the maximum flow that you have found, the flow value equals to the mean capacity of the cut value, then definitely, if you can show this feature, definitely, if you want to find out this solution, you may find out this solution such that it implies the solution. So we will talk about more about this feature later, but right now we have the definitions of these two problems. Question?
Yeah. So minimal doesn't imply that it's primal, and max doesn't imply that it's dual.
Exactly. It just you can say this is the primal, this is the dual.
Okay.
So it doesn't matter whether you maximize or minimize. Any other questions? So let us look at the solution of the maximum flow problem. So right now, let us focus on this problem. And when we talk about the solution to this problem, eventually you will stuck there. And in order to find out the solution, we need to look at the dual problem in order to have more insight. So right now, let us look at the maximum flow problem and look at the Foxman algorithm. So the maximum flow problem is that initially we have the capacities of those edges. We have the source, we have the sink. And we know that the initial flow, which is the smallest flow, will be the zero flow. What does it mean? It means like we put 0 to the flow values for all the edges. And it satisfies the restrictions. One is the capacity restriction. Say like the capacity, the flow value is less than the capacity. And of course that the capacities are positive. And therefore the flow value 0 will be less than the positive capacity value. That's fine. Another criteria is that the incoming flow equals to the outgoing flow for any intermediate vertex. So we realize that the incoming will be 0, the outgoing will be 0. That's fine as well. So what is the algorithm that we are working here? We can take the greedy approach. And actually this is called the greedy, but it is different from the original greedy approaches that we have practiced before. And this type of approach sometimes is called iterative iteration method. What does it mean? It means like you initialize from some initial solution, and you try to optimize the solution until you stop and until you can improve it further. It's more like that you ask some money from your mom, right? So you ask your mom, give me $1, your mom give you $1, and give me another $1, give me $5, until you say, give me $7, your mom said no. And you know that at that time, this is the best money that you can get asked from your mom. So iteration method works in the same way. So we start with some feasible solution and we try to improve it step by step, and until we stop off. So we start from the 0 flow and we try to improve the flow, and then whenever we improve flow and we stop. So the algorithm could be written in the following way. Maximum flow algorithm. Initial 0 flow, and well, we can improve the flow F, then we improve the return So we didn't say like this is maximum flow scheme. We didn't say it's an algorithm because it's not precise. It's not precise. It's just like give a skeleton how we generate the algorithm. Well, we initial our flow with value 0 and let us the flow to be n. And there's the while loop. So whenever we can say like we can improve the flow, then we improve it. And the question here is that what do you mean improve a flow? And how will you improve it? So there are two questions that we haven't. Well, if we can, so we can improve the flow, then we improve it. So there are two questions that we haven't answered here. Is that how do you identify that the current flow could be improved, right? So given a flow, can you let me know that whether it could be improved for a while? And if you can, then how do we improve it? So there are two questions that we need to answer for this particular scheme. So one way of suggested by the greedy algorithm is that if we can say that we can improve the flow, and if you can imagine that the flow network is like a water path network, such that you have the source and you have the thing, and then none of the intermediate nodes will generate water. So you will see like, okay, if I want to increase the flow, then I want to push some flow from the source to some vertex, push some flow along this edge, and then push some flow to the thing. So it means like whenever you are able to push some water from the source to the thing, then there must exist a directed path from the source to the thing, such that you push such a flow along that edge, and the flow capacity, the capacity restriction is still satisfied. And whenever you can find out one path, that you can push the flow from the source to the thing, then you will do this. So we expand this sentence by saying that find path, okay, from the source to the thing T, such that, okay, such that there exists a remaining capacities of all edges that we can push flow on. So look at this. This is the path, right? So we know that we can push flow up to 10 units along this edge. And we can push flow up to 4 units along this edge in order not to avoid the capacity restriction. We can push up to 10 units flow along this edge. So if we push some unit flow along this path, then what is the best units of water that we can push along to? 1? 4. Great. So this is the bottleneck edge along this path. You can push 10 units here, but if you push 10 units into this vertex, it need to pull out the 10 units, right? So we push, let us say we push A units here, A units going out of that edge, that vertex, and A units goes out of that vertex. And for here, A should be no more than 10, A should be no more than 4, A should be no more than 10. So this edge is the bottleneck edge. It determines that how much water that you can push from the source to the thing. So we can push 4 units here. And then we can push, after we push 4 units up here, let us show the figure. then we know that we push 4 units along this edge, 4 units along this edge, and 4 units along this edge. After we push 4 units along this edge, we understand that this edge is saturated. You cannot push more flow along this, right? So this edge is removed from the graph when you are looking for another path to push the flow from the source to the sink. And then let us look at another path from the source to the sink. Then look at this path. Here is 10, capacity is 10. Here capacity is 9, here capacity is 10. Then what is the best that we can push along this path? 9, right? So we push 9 here, we push 9 here, we push 9 here. And we realize that this edge is saturated. You cannot push more flow to it. So this edge is removed from your consideration, right? So you don't want to consider whenever you select another path. Then we realize that for this vertex, this edge is disconnected, right? For this vertex, this edge is disconnected. So there's another path from here to here. Okay, you cannot go here because this edge is from here to here, here to here, and here to here. There's another path, right? So what is the best value that we can push along this path? From here to here. 1, right? So here we updated to 5, we updated to 1, we updated to 10. So this edge is saturated, this edge is removed from our consideration. And after you push so much flow, you realize that you cannot find out any path from the source to the sink, right? And particularly for this instance, you cannot find out any path from the source to the sink. Then you stop. Right? When you stop, then yes.
Don't you still have one more back?
Which one?
S to the top of the second column diagonally down.
You mean this one and to here?
No, on the 8.
Yeah.
Then up,
And then up.
straight up and diagonally down.
Okay, great. Sorry about I missed one thing. Okay, let us try this path. This is we can push 5 units here. We can push 7 units here. 6. Then how much we push? 5, right? So let us. This is 210. Here we add 5. That is 6. Here we add is 5. Here we add 6. Great, thank you. And also, let us see which one is saturated. Did I? Yeah, the program. This is the saturated. So did you? Can you find out one more pass from the source to the sink? All right. So we start. And if we start, what can we do? So that will be the correct answer to the maximum flow to this particular problem. So if we look at the problem, then this is the flow out going from the source, 9 plus 10, which is 19. Is 19 the correct answer to this problem? We don't know yet, right? And maybe this is not the correct answer. Eh? Did I miss something here? Maybe we choose different approaches which results in the optimal solution. But let us look at what are those things. They choose different approaches. Let us get this downside and then we look at it. Okay, so just now we use a different set of paths to update the flow. So it doesn't mean like each course of the update will result in the same value. So we look at what are the solution provided by the slides. Okay. The very first pass for this network is to select this pass, and the bottleneck is this edge. So they push 8 units of flow along that edge, resulting in 8, 8, 8 as the flow. And another pass is this one. So here the remaining capacity is 2. Okay, here the capacity is 2, capacity 9, capacity there is 2. So remaining capacity is 2. So you just push 2 units here. So this edge is saturated. 2 units, this edge is saturated. 2 units and 2 units there. Another path is like this. You select the 10 units capacity. This is 7, right? So here is 6. So here there's 6. So 6 is the bottleneck. So you put your 6 units flow along this path. You have to do like this. Okay. So let us look at the flow got from the algorithm. Okay, which is a different sets of paths to find out the flow. The same algorithm, but different paths to find out. Then we realized that you can now find out, let us see, this edge is saturated. So it seems like this is the set of edges that you cannot push more flow from the source to the sink. And then if you remove these edges, then the graph is disconnected. So it turns out that there's no more path that you can push flow from the source to the sink. And turn out that the ending flow value is 16. Well, the optimal value is 19, and we also got 19 from another set of steps to calculate the flow using the same algorithm. So what does it mean? It means like the algorithm itself, sometimes you cannot find out the optimal solution. It may determine the number of, it may determine the paths that you have selected here to improve the flow. So which path you would like to improve the flow? And the improve the flow is relatively straightforward. You can improve the flow by selecting the bottleneck edge and then push the flow up to the residual capacity of the bottleneck edge. So this part is clear, but this part is unclear. But based on what we have seen here, if we select the path without any restrictions, we just select the path to see whether we can push flow along it, and then sometimes it cannot result in optimal solution. So the greedy approach, particularly the iteration method approaches, discussed here is not optimal. Okay. So we want to guarantee it's optimal, then there are 2 options. One is that we design a way to find out the path, like the one that we just calculated, such that you can guarantee that following this way of selecting the path, you will end up optimal flow. Another option is that maybe the approach that we have worked on here is incorrect, so we need to modify the approach in order to make it better. No matter which path, which sequence you select the path. Question?
Can't we start from the end and work backwards?
Yeah, you can, but it doesn't, if you can generate the optimal solution from here backwards, right? So you just swap with from the source and the thing.
Oh.
So you will generate the same solution in the original one, right? Right?
Yeah, I guess.
Have questions? Okay, we have so the iteration method doesn't work. The iteration method doesn't work. So we need to think about those 2 options. The first option is that we define the sequence for us to select the edges, to select the path in order to improve the flow.